In this lesson, we're going to look at some periodic trends. We're going to focus on the atomic radius, ionic radius, and the comparison between the radius or the size of an atom or ion for a particular element. So just to start with, if we look back at the periodic table, we have talked before about how the elements are arranged in a way that elements that are in the same group have the same number of valence electrons, and because of that same number of valence electrons, they behave similarly to one another. We have talked about elements in the same row having the same number of shells of electrons, and so we are going to use those and some other things to help us explain some different trends that we see in the periodic table. So this is a good summary of some of the different trends. In this lesson, we are only going to focus on atomic radius, ionic radius, which is the same trend as atomic radius, and then comparing the size of an atom versus ion for a particular element. So the rest of these we'll look at in a different lesson. So atomic number, remember the atomic number is just the number of protons in the nucleus, and the number of protons, or the atomic number, is what tells us what type of element we have. So we can have a different number of electrons. We can go between a neutral atom or a charged ion by changing the number of electrons. We can have isotopes, which would have different numbers of neutrons for a particular element, but if the atomic number changes, if the number of protons changes, then the element is no longer the same. So the periodic table is arranged in order of increasing atomic number. So that means that as we go across a period, so as we're moving in this direction along the periodic table, the atomic number is going to increase, so each element to the right of another one is going to have more protons than the one before. And then also as we move down a group, the atomic number also increases. And so, oops, just going to switch pen color here. So in the periodic table, as we move, we start with one proton, move across two, and then we come back to the next row, 3, 4, and so on. And so we are constantly adding one proton, so our atomic number is increasing by one, and then we come down to the next row. And so because we're always increasing in atomic number as we move this way, then when we say we move across a period, our atomic number, our number of protons is always increasing, and then also as we move down a group. So when we talk about our trends, we are going to talk about moving across a period. So from left to right, is there an increase or decrease in a particular trend? And then down a group. So as we move down the group, is there an increase or decrease in that particular trend? So the atomic number, because the protons, as we said, increase as we move across and then down, that's where we see an increase going across and down a group. So those are both increases, those trends. So atomic radius, this is just the measure of the size of an atom. So we're looking at from the center of the nucleus out to the furthest valence electron there is. So that is going to give us the atomic radius. So the radius of an atom, which means equal electrons and protons, so a neutrally charged particle. So the trend that we see is as we move across the period, there is a decrease in the size, and as we move down a group, there is an increase in size. So the increase as we move down a group is probably not particularly shocking, as we add more protons and more electrons and more shells of electrons. It's probably not very surprising that the size, the atomic radius, is going to increase as we move down the group. But as we move across a period and we add more protons and electrons, we actually see a decrease in the size. So we're going to take a look at why. So this just gives us an idea, a visual representation of that. So we can see if I look at any one group as I move down, there's an increase in the size. This one is probably not surprising. But as we move across a period, what we see is that the size of the atom actually gets smaller. So why is that happening? So the group one, once again, this one's probably not very surprising. So as I move down a group, I add another level of electron, so another layer or orbital. And because of that, it's not surprising that the radius is going to increase. So the period, when we move across that, the reason that the size is actually going to decrease. So there's no change in the number of shells of electrons. When we're in the same period, there's the same number of shells. So here, every single atom here has 2 shells of electrons, which means it's going to be found in the second period or the second row of the periodic table. And as I move across, I'm increasing my atomic number or my number of protons, and then also my number of electrons. So you may think because we have more particles that is going to result in a larger size, but there is a lot of empty space here. And so the electrons can get pulled closer into the nucleus, and that is what happens here. And the reason that that happens is as we keep the number of shells of electrons the same, but we add more protons in the nucleus, we have a greater charge in the nucleus. And so as we have more protons, stronger force pulling those electrons in the shells towards the nucleus. So as we increase the protons, the nuclear charge, or that force of attraction between the protons and the electrons, also increases. And as we have that stronger attraction, those electrons are pulled in more tightly or closer to the nucleus. And so that's the reason that even though we are adding protons and electrons as we move across a row or across a period, here the size of the atom is actually going to decrease or get smaller. So the ionic radius, same idea, only for an ion, electrons have either been gained or lost. So we're still talking about the distance from the very center of the nucleus out to the furthest electron in the valence shell. So same idea for what the radius is measuring, but here we don't have a neutral charged particle. What we have is either a positively or negatively charged particle. So the atom has lost or gained electrons and is now charged. So and I don't think I covered this in atomic radius. PM or picometers is what we measure that distance in for atomic and ionic radius, and that is just 10 to the negative 12 meters, or if you take 1 meter and divide it by 10, 12 times. So that's what 1 picometer is. So the trend that we see for ionic radius is actually the same as for atomic radius, where as we move across the period, there's actually a decrease in the ionic radius. And as we move down the group, there is an increase. So once again, the down the group is probably not surprising because we are adding more shells of electrons. And I've just popped this here because we do have one blip in the trend and then it continues again. So we're going to focus in on that one specifically. So what happens when we move across? So we'll start with a visual. This shows the ionic radius for multiple elements here. And so we can see that as we move across, they get smaller, and then there's a jump and they get bigger, and then they get smaller again. And so that same trend happens as we move across the periods. And if we look at any group and move down, we can see that there's an increase in the size. So once again, the increase in the size is probably not particularly surprising. Every time I move down to another row, there is another shell of electrons added. So it's not surprising that the radius is going to get larger as the electrons are in another orbital further away from the nucleus. With some of these blips here in terms of the moving down, we're not going to focus on those this year, but in the 4U course, we'll talk a little bit more about electron arrangement and explain some of that. So the downer group, once again, probably makes a lot more sense. The further you move down the group, the more shells of electrons there are, and so the radius is going to get bigger there. And then as you move across a period, we have a decrease because the atomic number, as that's increasing, so this is the same idea as with the atomic radius. So because we have more protons, we have a stronger force between the protons in the nucleus, the positively charged protons, and the negatively charged electrons orbiting in the shells. And so that stronger force of attraction pulls those electrons in closer. But we did see that there was a jump partway through. So I think this last part is just the exact same as what we had before. So as the number of protons increases, the nuclear charge also increases, and then that means the electrons that are in the valence shell are attracted more strongly to the nucleus, so they are pulled in closer. But then we had that blip happening, and so halfway across the period, there was a jump up in the ionic radius. And that's because there is an extra energy level happening at that point. So if we think about the first half of the periodic table, when we're talking about group 1, group 2, and group 3, those have respectively 1, 2, and 3 valence electrons in that outer shell. And so anything in group 1 is more likely to lose 1 electron than to gain 7. So when something in group 1 loses that 1 electron, this was the valence shell. The electron from there is gone, so it has 1 less shell than the atom for that element. So if we pick lithium, for example, which has 1 layer of electrons and then the valence shell. So once that valence electron is gone, once that valence electron is gone, we'll just draw that back in, and the 1 electron leaves, we're left with only 1 shell with those 2 electrons. And so we have the 3 protons in the nucleus and 2 electrons, so this has a charge of 1 plus. So it has 1 less electron shell than what it had before. And so for the groups that become positively charged, they are going to have less electron shells, or shells of electrons, than the, sorry, can't do 2 things at once here. They're going to have less shells of electrons than the second half of the period where here the elements are gaining electrons. So as we look at that blip where the radius got smaller and smaller, and then we had a big jump, and the radius of the elements in the second half of the period were quite a bit larger than the first half, but within them we still saw a trend where the radius got smaller in the first half, and then we had a big jump, and then as we compared those to one another, there was still a decrease in the radius. So same idea as for atomic. As we move across, we're adding more protons, which is increasing that charge, the attraction that is between the positively charged protons and the negatively charged electrons, and that pulls the electrons in tighter. So that's what happens from here to here, and it's also what happens in the second half of the period. So as we move along, there is an increase in protons, and that means an increase in the charge, pulling the electrons in more tightly, making the size of the ion smaller. So this big jump here is because lithium, which the atom would have 2 layers of electrons, the ion only has 1. And so as we move across the period, once we get to nitrogen, nitrogen had 5 electrons originally, and it is going to gain 3 electrons and then have a charge of 3 minus. And so these ions are in the same row in the periodic table, but lithium as an ion only has 1 shell of electrons and nitrogen has 2. So that's what accounts for this big jump. As we move from this element to this one, there is an extra shell of electrons happening there. Okay, so the last trend we're going to look at is within one element, making a comparison between an atom and an ion of that element. So we were just talking about lithium, and lithium, when it's an atom, has 2 layers of electrons, so it's in the second period, so 2 electron shells. But when it becomes an ion, it loses the 1 electron in the outer shell and then has 1 less shell. So if we look here, the dark gray is the ion size and the blue is the metal as an atom. So lithium as an atom is larger than as an ion, and that is just because we have a loss of electrons and electron shells happening there. So that's true for all the metals here, as we can see. And then as we look over at the non-metals, where these are going to be gaining electrons. So once again, the gray is the ion, and then that lighter brownish gray is the atom size. So over here, as we gain electrons, we're not increasing the number of protons to increase the charge from the nucleus, but we are adding more electrons in. So here, as we add more electrons in without changing the number of protons, so for one element, here we have a larger size. So the size of an ion compared to neighboring ions, and then also the size of an atom compared to an ion for a particular element, is going to depend on whether there is a gain or a loss in electrons. So just a more detailed look. So lithium here, the atom is larger than the ion, and that is just because the outer layer, the valence shell of electrons, are going to be lost, and so we have 1 less shells of electrons. So all cations, because they are losing that outer layer, are going to be smaller as ions than as atoms. And then the reverse is true of anions. So here, there's no change in proton number, so we're comparing the same element, but we are adding more things into that outer shell. So we're adding more things that need to get pulled in without increasing the force from the nucleus that can pull things in tightly. So because of that, anions are going to be larger because their number of shells of electrons stays the same, but then they're adding in more electrons without increasing that pull from the nucleus.